So last time, we left off talking about related rates. It looks like my weekly schedule still hasn't updated. I don't know why it's not doing this. Let me try one more time. Refresh. Oh, it's not working. So there's some homework due. So there's homework due on Monday, and there's some more due tonight. It's related to the things we looked at last week. So implicit differentiation is one of those things, and the mean value theorem. So really just a couple pages of notes. These 2 pages of notes are what you need for the homework tonight. I also looked at one of those. I'd be happy to look at some of those. Maybe we could do that to start, actually. That'd probably be the best idea. Does anyone have any homework questions that you want to look at to start? Because what we're working on now, this related rate stuff, uses implicit differentiation. So it'd be good if we had that clear in our heads a little bit before we kept going. Thoughts about any of the homework or anything that's due this evening? Okay. I plan to look at one of the homeworks from this related rate section. So maybe that'll help with the homework that's due tonight too, if you haven't started that yet. Anyway, we were looking at this related rates page, right? And so it uses implicit differentiation. That's why we started with this implicit page and then moved into that. And as a reminder, since we're going to use this in the material today, we're thinking about this implicit differentiation. Let me do a quick summary here, kind of a quick and dirty summary in case this is really confusing. This is my implicit differentiation kind of quote unquote summary. It's like if we wanted to take the derivative of something like this, say, let's say we had like x squared plus 2x plus 6, and that's being squared or something like that. And we wanted to do d over dx of that, right? That would be a chain rule. And this one's not too bad, and we know how to handle ones like that. But you could imagine that what's inside there might be some really nasty thing. And so let's say instead of having just that nice polynomial, just imagine it's something really bad, some nasty function that's really hard to deal with. But we know it's a function of x. So it might be helpful to, instead of having that in there, because maybe it's really long, it's really taking up a big amount of space, or maybe it's just really hard to think about, or maybe, it's not really important and so you don't want to look at it, whatever it is, you could kind of think about taking that out and just writing a y in there, where y is the thing you just replaced, right? See what I'm saying there? So it just kind of like simplifies the function a little bit, or the process we're doing. And instead of having some really big nasty thing in there, we just say, okay, well, there's something in there and we'll just call it y. But we see that y is actually a function of x, right? And so if we go to do the differentiation there, it's still going to be a chain rule because y is a function of x, right? So still a chain rule because y is a function of x, right? We're just kind of like hiding it inside of y. And so that's what we're thinking about, very similar kind of process when we look at problems like these, for example, that we looked at last time. So I'm just going to kind of zoom in on this one right here. Right? If I look at that part that I've highlighted, we're thinking about the y's as having t's in them in this particular problem. And so we're kind of like hiding their true form, very similar to the way we think about hiding their form right here, right? We're just sort of like disguising it, right? And so that means when we take the derivatives, like this one that I'll highlight, for example, even though it's just y squared, y is itself a function. So it's like some other thing that we've removed. And so then, therefore, the chain rule still applies, right? That's what we did right here, is we use the chain rule. And so that's the way you want to be thinking about these implicit differentiation things, is these variables, some of the variables are themselves functions. And we might think they're functions in this kind of way where, oh, we had something that looked like this, but we just rewrote it to maybe make it look simpler, but it's still a function itself. That's sort of the way we're thinking about it. And hopefully it'll become a little more clear as we keep going through these applications, right? So the one we looked at to start last time was sort of talking about, oh, well, we have this equation for area. I'm going to use another color because I've already got that one there. I'm going to start highlighting in green. We have the function, the equation for this area of a circle, but the radius is changing, right? So the radius is itself is some function of t. So when we do that differentiation, if I just kind of zoom in here, again, it's a chain rule because we're doing d over dt, and the r part of that is hiding some t, right? It has some function of time, and we don't know what it is, right? So it's very similar to this. It's like this last situation where instead of having this, we don't even have that to start with. We just have this where we know what's in there as a function itself, and we don't know what that function is. And so when we differentiate it, you got to treat it like a chain rule. So that's sort of, that's sort of a quick and dirty summary of implicit differentiation and relating it to these kind of ideas of, hey, we have some equation and something in the equation is changing. And so that's what necessitates implicit differentiation. All right, that was a just kind of quick summary of what we did last time and where we're at. Can I clarify anything I said there? Okay, so in these actual applications, these related rate problems, the things that are changing are the things that are functions of time in this case. And so here's a real application. These are the real kind of problems that, if we get good at calculus, these are the kind of things we can solve. So we've got a boat being pulled in towards a dock, right? It's describing that picture. And it's being pulled in by a winch, right? So someone's like cranking a winch, or maybe it's motor powered. And so if you kind of look at this picture, this piece right here is pulling the dock in, right? It's pulling, it's like a rope that's pulling it, obviously. Okay. And so it creates a right triangle in this situation though, right? Because this part's moving, the rope, and as that moves, it actually causes the boat to move closer towards the dock. And then the boat is a certain height off the dock, which in this case is 10, right? To kind of get the scenario there. And so if we think about what's moving and what's not moving, a couple of those sides of the triangle are changing. And so those are going to be functions of time. That's sort of the way we're thinking about this. So I'm going to redraw this picture in a larger way here. And actually, can I just throw in triangles? They don't have triangles, huh? There must be triangles out here somewhere. Anyway, I'll just draw a triangle. I'm going to draw a bigger triangle that describes this system. All right. Just wondering if I could do something like stick a boat in there. No, not those kind of images. Sticker. Waste too much time looking through this stuff. Any boats in there? All right, let's stop wasting time. So the boat's down here. And let's label the triangle. It's a right triangle. And so we can label the sides A, B, C. Very typical way to label that triangle. And the winch is up at the top here, right? All right, and it's pulling the boat in. And so two of these sides are changing. C and A are the sides that are moving, right? And side B is fixed. So let's go ahead. I'm just going to zoom in on this picture and keep labeling it based on the information here. So we know that B is 10, right? Because it's 10 feet off the dock, if you look at the description there. And the question is, at what rate is the boat approaching the dock when the boat is 50 feet out? Right? And so what's changing in this picture? This is moving and this is moving. These two sides are moving. And what we want is we want this rate. Guys with me on the picture? All right. So two things are changing, right? The two things that have the arrows on them. And so that means C is a function of time. And so is A, because they're changing, right? They change over time. And so that means you can take derivatives on them, right? But B is not changing. And so we want to eventually get the A prime rate. That's what we want, right? We want the rate of change of that side, which is the derivative. So maybe let me make that clear. So we want this rate. In other words, we want to find A prime of T. We want to see how the side A is changing over time. That's what the question is asking us. And we know what C prime is, right? What piece of information tells us C prime? Anyone?
Is the 30 feet per minute?
Yeah, right. So the winch is pulling 30 feet per minute. So that's telling us that this is the 30 feet per minute. What's B prime? So we want to find A prime. We're told C prime. That's the winch part. B is just the distance from the winch to the boat, which is fixed. That's not changing over time. So what's the derivative of a constant?
0.
0, right? B is 10. B is not changing over time. It's not a function of time. And so if we take the derivative, it's just 0 because B is not changing. It's not a function of time. That's what B prime equals 0 means. It means the rate of change of B is 0. It's not changing. You with me on this, the figure? So the way these kind of problems all work is we need a way to relate the sides or the information we're given. In this case, it's sides of a triangle, right? Or sides of a right triangle. And so that's what the confusing part of these problems is, because even if we have a nice picture like this, we might not come up with the right equation to use. But with a right triangle, there's not too many options, right? It's either going to be like a SOHCAHTOA thing or Pythagorean theorem, something that we can relate the sides. And hopefully you're with me on if we need, let me make this a little bit thinner. If we need to relate the sides, A, B, and C of a right triangle, it's really begging us to use Pythagorean theorem. I'll probably need to go on another page anyway, so I won't bother cramming things in. Right? And specifically, A is a function of time. C is a function of time. And B is just constant. So when we take a derivative in a second, B is just going to go away because it's constant, right? All right, you guys with me so far? I'm going to add a page here and so I can keep writing big. Let's see. So, we want A prime. Right? We want the derivative of A. And so we're going to want to get A prime out somehow, which means we want to take a derivative. And so we're going to take a derivative of that equation, right? So we're going to do d over dt of A of t squared. We'll do d over dt of just B, which is just a constant. And then we'll take the time derivative of C. And so when we think about it like that, right, then we see, oh, okay, well, we have a constant rule and a chain rule because of implicit differentiation, kind of similar to what we've been looking at in the past, right? So this is going to be chain rule, just like we've been seeing. So is the last one. And then the middle one's just a constant rule. So it's just going to be 0.
That's the derivative of the Pythagorean theorem, right?
We're trying to take the derivative of the Pythagorean theorem, yes. And the reason I knew to do that is because of what we're trying to find, right? Let me highlight the thing we're trying to find here. We're trying to, let me do it in yellow so it stands out a little more. We're trying to find a prime of t. We want to know how quick is the boat going towards the dock. And so that's a prime. And so I want the derivative of a. So I'm going to take the derivative of this equation, and it's going to give us an a prime. And then we'll be able to plug in some of the things we know and find out a prime. Other thoughts about the setup so far? Okay, so I know we just did implicit differentiation last time, and people haven't worked on that homework yet. So, but these two things right here, this a prime squared and the c prime, or sorry, the a squared of t and the c of t squared, those are very similar to these things we did last time, right? Like looks just like this, for example, right? A squared would be exactly that. And so how do we do that? We thought about it as a chain rule, and it became this. See that? Bring down the power, subtract 1 off the power, multiply by the derivative of the inside. Right? That's the chain rule. And so each one of those terms is going to be this exact thing. So I'm not going to go through those details. Just know that this is what we did last time. And so you can look up there if you want to see how to do this one in detail. Right, so let's go ahead and keep going. So this then becomes 2a, here I'll put the a of t still, times a prime of t. Right, that's the chain rule. The b just goes away, and then we get 2c c prime. Right, those are the chain rule. Is that okay? The derivative look all right? That's just based on what we did last time. Yep.
Do I have to write a as a function of t, or can I just say 2 times a times a prime?
Yeah, you can write 2a prime. That's how I actually wrote it in my notes. I'm just trying to be clear that they're functions of time. But yeah, I'll just write it like this too. Yeah, 2a prime. Other thoughts? Seems okay. So remember, the goal is we want a prime. Sorry, was someone going to say something?
I was going to say, if we know that C is 30 per minute, why don't we just put that in from the jump and then just do a power rule instead of a chain rule? Or does it not work like that?
So look at, yeah, it's a good, whoops. So we're going to use that information in a second. This is the question here. The information we have, though, is related to the derivative, right? And so this piece of information is going to go into this part. And that didn't come out until just now. Right? Okay. It's not what C is, it's what C prime is. See that? We actually don't know C. That's exactly where I'm heading, though, actually, right? So let me just review where we're at. I don't know if that helped. I didn't hear a response there. Let me know if that didn't help. But we want to find A prime. Right? That was the goal. And we were given the distance of A. Right? We're being told this happens when A is 10 feet out. So we're being told that, I'm sorry, that's the wrong thing I highlighted. We're being told that the A is 50. Right, so we're being told that A is 50. And so we want A prime. We're being told A. We know C prime. Right, that's what we just pointed out. So we have almost everything we need. We need to find C. How do we know what C is? We were given this piece of information. We know that this side's length 10. We want this side. We know this side's length 50, right? We can find C. Confident everyone can do that and get C is the square root of 2600. which is approximately, it's almost 51. Thoughts on that? Does that seem okay? So now we have all the pieces of information we want, right? We want to use this formula. We have A, we have C prime, we have C. We can plug all those things in there and get A prime. And so we're done pretty much. But are there questions about where we're at here? We'll switch over. So we have this equation, 2A prime equals 2C C prime. And we have all those pieces of information. And so that's, let's see, A was 50. We want A prime. C is, I'm just going to put it in as 20 square root of 2600. And then C prime was 30. And so we can get A prime. So just divide everything over and we get the answer. And if we plug it into a calculator, it's about 31 feet per minute. All right, let me see what you think about that. I'll summarize in 1 second here, but are there specific questions? Kind of reflesh it out. Right, so the idea is the winch is pulling the boat's moving towards the dock. We know how fast the winch is moving, but we're using that piece of information to figure out how fast the boat is moving. And so it turns out when the winch is pulling 30 feet per minute, that the boat is going to be moving a little bit quicker because it's the shorter side of the triangle, probably is the short there. So it's 31 feet per minute. And the way we came up with that is we created this diagram here, right? This diagram on the left that set up the situation. We knew we wanted to relate these three sides because we know we want to figure out A prime, and we're given things about B and C, right? So we're like given like some pieces of different parts of the triangle. And so the way we relate sides of a right triangle is Pythagorean theorem, right? That's how, this is the confusing part usually. It's like, even if this all makes sense, how do we know to use A squared plus B squared equals C squared? Because we're trying to make, logically think about what we're given and what we're trying to do. We're given pieces of a right triangle. We're trying to find one of the rates of the sides. And so it just sort of makes sense to use this equation. We identified what was a constant and what wasn't, right? That was this part. We figured out that B is just a constant, but the other two are changing over time. And so we're going to need chain rules on those. And, to be clear, the chain rule is using implicit differentiation, the thing from the previous we did last time. We did those things and got this expression. And then we just we tried to figure out what we had and what we wanted. Right? We want the A prime. We're given A and C prime. So we needed a value for C. The other sort of thing to think about is, to that point, we'd used all the information so far except for this part. And so where does that come in? Oh, well, that came in this part where we put that on the triangle and figured out the third side. right? And that gives us that third side. And then we have all the pieces we need. Again, we want this piece right here. We then had all the other components. We just plug them in and solve for that one piece. All right, can I clarify something about that? So this particular homework I set, maybe while you're thinking about that, it's due next week. I just opened it up today. And some of the problems look pretty different than this. So I'm going to look at maybe one of those problems. Just see here. Remind myself what's in there. So there's a couple of them that kind of look like this kind of problem where you're setting up a real world application and thinking about what's going to happen there. Yeah, so there's like 2 or 3 like that. And I'm happy to look at some of those in class maybe next week. But I just wanted to do a sort of a slightly different one from this homework set that we haven't represented yet. So maybe one that looks like this or this, say. So this is like related rates problem number 1. And the information we're given in this is this equation, xy equals 1. So I'll just write that down right here. But we're being told that both x's and y's are functions of time. And so this is really x of t times y of t equals 1. Okay. And so then if we're going to do, let's read the problem. Actually, I'm kind of just jumping right into it. It's telling us that the equation, it's telling us dy dt, and then we want dx dt, right? When x is 3. And so we're doing the same kind of thing. So we're going to, what this is telling us to do, the process is 1, do d over dt of both sides. 2, plug in the given info. 3, solve for what you want. So it's the same process we just did, and it's just simplifying it because we don't have to like derive the formula or anything like that. It's just like giving us the formula. It's almost like we're doing this last problem, but we're starting right at this point. We're just like given the formula and we're just going to roll with it. All right, so I'm going to do this one and I'm going to ask you to maybe think about the next one. I just want to make sure that this process is kind of clear. So number 1, let's do d over dt. So if we take the derivative of both these things, on both sides, I mean, take a second and think about what rule we're going to use here. Both these things are functions of time, x's and y's. One is not a function of time. And so when we do the derivative of 1, that's just going to be the constant rule, right? What are we going to do on this piece, though?
Product rule?
Yeah, that's a product rule, right? So we would have 2 things being multiplied, and we're assuming that both of those things have a hidden t inside them. And so if we're d over dt'ing them, it's a product rule. And so hopefully this makes sense, right? I'm not going to do all the details here. It'll be f prime, here, I'll write it like this, dx dt f prime g plus f g prime. Right? That's the product rule, and then we just get 0 on the right. That's what the product rule would look like. And I'm writing the derivative as dx dt or dy dt because it kind of matches up with the kind of information we're given, right? Because then we're being told you want this piece, you're being told this piece, you're being told this piece. How do we find out why? Thoughts? We need a value for y in order to move forward on this. Very similar to the last problem. Right? On the last problem, we were given some of these pieces, but we didn't know C. And then we used some other things we were told to find C. So what can we use that we're told to figure out what y is?
Can you use the part where it says x times y equals 1?
Yeah, right. So we know x times y equals 1, and we know x is 3. And so that's how we can figure out what y is, right? So Very good. Let me switch on another color here. So the way we find y is because we know x times y is it 1? Yep. And we know x is -3. So that means y times -3 is 1. That means y is -1/3. And so we can just plug everything in. Now we have something for y, and we can plug things in and find what we want, right? So let's see, dx dt is what we're trying to figure out. X is -3, dy dt. Okay, so this ends up being dx dt times -1/3 plus -3 times -1 equals 0, right? And then we can solve for dx dt. It will be -3 times -3, which is 9. I'm skipping some algebra there, but you can think about that. I think that's correct. So it's the same thing we just did, it's just doing it a little simpler. The ones towards the end of the homework set are the more difficult ones, and we can look at some of those next week. Your thoughts about what I was trying to say about this one? I'm gonna let folks finish writing this down, because then I would like you to try one yourself, and that way you can do 2 of the homework problems. We'll just get a couple of them out of the way while we're at it here. How are we doing on time? We're doing great. Thoughts about this one? Oop, just see this question. How did you know to set it up like that with the dy dt y, etc.? I think the question, are you asking a question about the product rule specifically? Like, how did this become this? Is that what you're saying? Yeah, and no. Can you clarify? Yeah, I'm not really sure what the question is, but the idea is we started with this. We're being told that x and y are functions of time, so that's how I moved to this. And then we wanted, the question is specifically saying, what is dx dt, right? And so that means this is telling me we should take a time derivative then. If we want to figure out dx dt, then we need to get dx dt by doing a time derivative. Right, so take d over dt is what I'm saying. And so when I did d over dt of 2 things that have t's in them, that led me to realize it's a product rule. Right? It'd be kind of like if we had like t squared plus 1 times 2t minus 1 or something, and we wanted to take the time derivative of that. That's this situation. It's like this is our x of t, this is our y of t. Right? If we did that, it would be a product rule. It's just that instead of having the thing on the right, we don't have this thing. We just have like this version of it instead. And so, there's t's inside the x and y's. We're kind of thinking about them, right? Like if we had something like this and we did d over t, hopefully you see that's a product rule. It's the same kind of thing here, because we're doing the time derivative and there's t's inside there. I don't know if that clarifies it, because I wasn't super clear about the question, but does that help out? Or does anyone else have a question? So I'm going to save a copy of this one into the homework folder. And then I'd like you to try number 5, which is similar. Actually, is number 5 similar? Did I want to do it differently? This is actually maybe too similar to this one. Thought this one might have been a little bit different. But maybe it's good that it's the same. So I'm going to just sort of pause here and let you try this one. So we have it's almost the same setup. So this one shouldn't be too bad, right? We have x, these two things are functions of time, equals 3. Right, we're going to do d over dt of both sides. And we're actually given kind of similar pieces of information, right? We're actually being told dy dt, we're being told x, we're going to use this to find y, and then we want to find this, right? So it's going to be very similar, actually. It's going to be another product rule. All right, let me let you just run through that one for a second. I'm going to stop talking, but if people want to chime in and let me help you, I would love to do that. I'm not going to bother doing a breakout room this time, but let me know if I can chime back in if you want to ask me something. You could send me a private message. I'd be happy to listen to you if you want to verbally express it. Maybe in a minute, I'll kind of slowly start writing things down. If you want to ask a question about the last one, feel free. So I've started it here with the product rule. It's the same setup as the last one, right? We'd have the product rule. And, I don't know if the notation is a little bit confusing. I know it's jumping around a little bit here, but let me just remind you that if you write something like dx dt, that just means x prime. It's just a different notation for the derivative. And the reason we're not just doing the prime in this case is because we're trying to be very clear about there's a t in there actually, right? It's not an x or an y in there, it's a t. And so there's a little bit different. There's 3 variables kind of floating around now. And so we have the setup, we have all the things we need except for y. We know x times y is 3 and x is 5. And so that means 5 times y is 3, so y is 3/5. Right? Excuse me, we can just plug that into the formula, find the thing we need. So what we have is dx dt, which we want to figure out, times 3/5 plus 5 times, what is dy dt times 1 equals 0. Easy enough to figure out what dx dt is. Just subtract the 5 and multiply by 5/3. So we'll have minus 5 times 5/3, which is minus 25/3. How's that look? Is that what you guys got for this one? I hadn't done that ahead of time, so you can check my work or see if you got the same thing. How's it look? Anyone get something different?
Can you scroll down a little bit? Thank you.
So from what you just had, how'd you get -5 times 5/3?
So we have x prime times 3/5 equals -5. Is that all right? Subtract the 5 over.
Yeah.
So we want to get rid of dividing by 5. So we multiply by 5 so that these cancel. Thinking about this in terms of steps. And then we divide by 3. Other thoughts? All right, if there aren't questions, I'm going to keep on going. And I've actually decided to move past this next topic. So this Newton's method thing I usually do in class with, I bring in like graphing calculators and we do it on a graphing calculator and stuff. And so I'm going to end up just skipping this section, unfortunately. It's kind of an optional section actually in the topics, the way it's listed. I really like it because I think it's cool. It's an application of derivatives. It's kind of like an easy thing in my opinion, but we're just based on the schedule and based on the fact that we're not in person and I can't pass you a graphing calculator right now, I'm going to skip it. So we're going to skip that and move on to page 51 here in L'Hopital's room. Sure, you guys would be broken up to learn that we're skipping that, but it's okay. It's okay. Now, it really is I didn't learn about Newton's method until I think grad school. So it's just kind of like a bonus thing that I'm just going to move past here. we are going to go on to 51, and I'm going to set this idea up here. My goal is, oh, Josh, it's okay. Hey, Josh, we'll meet later about this. Come to office hours, and we'll do an additional lecture for you, okay? Anyone? Seriously, if anyone's
Sounds
interested in learning
good.
about that,
That sounds
I'd be
great.
happy to show it to you. It's kind of a cool thing. It really is. But anyway, maybe my opinion about what's cool isn't relevant. Okay, so let's talk about this. This guy's name is L'Hopital. It's a weird person's name. I can't remember where he's from. I want to say he's from the Middle East somewhere. L'Hopital, does that sound right? Maybe he's French. I can't really remember off the top of my head, but
That
he's
sounds
a
great.
famous mathematician. Again, you pronounce that name. I've always heard it, L'Hopital. And he's got this rule that relates limits and derivatives. And so that's two things we've talked about, and it's actually a very useful thing. And so my goal here, like I said, is to probably just set this up today, and then we'll finish it off, I guess, on Friday. But what it says, let's talk about what this says here. We've got two functions, f and g, and they're differentiable, which means we can take their derivative. Remember, very few functions, there's those special cases where you can't have a derivative. And if you look back up at the derivative section at that, those would be situations where this rule wouldn't apply. Most functions that we're going to look at are differentiable, though. So anyway, we've got two functions. We can take their derivatives on an interval, and we don't want the bottom one to be 0 because it's in the denominator, right? And what this says is, if we're trying to do a rational limit and we get one of these two indeterminate forms, then it turns out the rational limit is the same as if we took their derivatives, right? So notice how the ones over here, there's no derivatives, but the ones over here, they're derivatives. And so, and it works with both cases. The difference between the first row and the bottom row is that the first row is approaching a number, so not infinite limits, and the ones in the bottom are infinite limits. All right, so it just says, like, if we have an indeterminate form in an infinite limit, 0 over 0, infinity over infinity, we can just take the derivatives and look again, and that sometimes fixes the problem. And so it's like another technique, you might call it, for infinite limits. And it comes up in a couple other places sometimes in Calc too, but we're going to look at it in these contexts. So do people see how this definition reads? Right? It's important that we understand basically what it reads. It says, if you get an indeterminate form, then the limit is going to be the same if you take the derivatives. So try that. Thoughts? Seems okay. And at this point, we want to be kind of good at taking a derivative. So I'm not going to, we're going to just take derivatives. I'm going to assume the rules make sense to you, and let me know if they don't. But let's look at this first one. So if we did this limit as x approaches 2 of sine of 2 pi over 4 minus x squared, if we just plug a 2 in, right, you always want to try just plugging the number in, you would get sine of 2 pi over 4 minus 2 squared, which is, of course, going to be 0 over 0. So we get an indeterminate form in this case. And so what L'Hopital's rule tells us is, okay, well, let's look at the derivatives and see if that fixed the problem. Right? So that had the indeterminate form. So L'Hopital's rule says, take the derivative of the top and the bottom, to do both the top and the bottom derivatives, and see if that fixes it. And so if we did that, we would get the limit as x approaches 2, right? The first one is a chain rule, and so it's going to end up being pi cosine of pi x. And the bottom one's a power rule that becomes minus 2x. Do those derivatives look okay? Right? It's a chain rule and just a power rule. And so now if we plug a 2 in there, it's not indeterminate anymore, right? So if we plug a 2 in, we would get pi cosine of 2x, 2 pi, excuse me, over minus 2 times 2, right? So we don't get 0 in either case, which is pi over 4. Pi over minus 4, excuse me. So minus pi over 4. What do you think? See how that worked there? So basically what this rule is telling us is that when you have a ratio, i.e. a fraction, and you get indeterminate form, it turns out that the ratio of the derivatives is the same as the ratio of the original functions. And so that's helpful in this case because you can just take derivatives. In some case, you need to take more than one derivative, and it'll move you forward in sometimes in some of these limit problems. So I'm just going to write a quick summary of what we just saw there. I tried to walk you through it in kind of like a thinking it through kind of context, but the summary would be we were originally trying to take this original limit, and it turns out using L'Hopital's rule, it's the same thing as taking the limit of the derivative. And the first one was no good, but the second one ended up being okay. And just to be clear, from here to here, we did d over dx of the top and the bottom. Thoughts about the process at all? Oops, sorry, I just saw the chat. For this rule, we take the derivative of the top and the bottom separately always. Yeah, so you're not doing a quotient rule, right? Let's look at what the rule says here, right? So when you're looking at the rule, you say there's something in the top, and then you're taking the derivative of just the top, right? And then there's something in the bottom, and you're taking the derivative of just the bottom. So you're not doing the derivative of the whole thing, which would be a quotient rule. You're doing just the top, just the bottom separately. Yeah, that's a good clarification. But again, just kind of looking at the definition, we want to be able to read the definition and say, okay, yeah, I see it says that. Right? It would be different. What you're sort of describing, what I think that you're trying to clarify is it would be like this if it was going to end up being a quotient rule, right? Or something like that. And then we would do the quotient rule. But that's not what it's saying. It's just saying do them separately. Right, long-winded answer here. Other thoughts? Thank you for that. That was a good clarification. Okay, so let me just show you this one more and then ask you to think about the last one, and then we'll break up for the day. Why is pi in front of the cosine? So the question about pi being in front of the cosine is because if we do d over dx of sine of pi x, this is a chain rule. And the chain rule is going to end up being pi times cosine of pi x. If you want to talk about that individually, be happy to, but we've been looking at derivative rules for quite some time now. And we really need, obviously this is like the first step of these kind of problems. So we can't be bogged down too much in doing a chain rule like that. So anyway, let me know if you want to talk about that. I'm just not going to go over all the details at this point in class. All right, let me look at one more. And then ask you to look at that last one, like I said. So this is an infinite one, right? So limit as x is going to infinity on this one. And you can see the instructions say, hey, sometimes you got to do it twice. And so what happens if we plug in infinity on this one? We'll have infinity times infinity over infinity. And so that's in a determinate form, right? So it helps realizing that we have the indeterminate form. So let's apply L'Hopital's rule. So apply LR, L'Hopital's rule. So let's take a derivative. And the derivative on the top now is going to be a product rule. Let me switch colors here. All right, so we're really going to look at the limit as x goes to infinity. Let's take a derivative, and we'll have f prime g plus f g prime all over 2x, right? So it's a product rule and then just a power rule. Is that okay? And let me just go ahead and simplify that. This becomes ln x plus 1. Someone going to say something there? See, someone's asking, is the value we got equal to the actual limit of the original? Yes, the value of the final value in the previous one, pi over 4, is the original value of the limit, the original. It's both, right? What this thing says is the original limit is equal to the same as when you take the derivatives. What are thoughts about this one that we're on right now? Seems okay.
I have a quick question, Professor.
Yep.
Right where you did the product rule, where did you get the W of X in the first half of the
So that says
numerator?
ln x. Let me rewrite.
Oh, okay, my bad. Sorry about that.
ln x.
Thank you.
Other things. And so what I'm trying to point out is we did the L'Hopital rule one time, right? We took a derivative, simplified it, but it's still indeterminate. If we plug in infinity here, we still get infinity over infinity. Ln of infinity is infinity. 2 times infinity is still infinity. And so what we can do is this is in the same situation we were just in a second ago. And so we can just do L'Hopital's rule a second time. And this time it's going to work. Right, so just take another derivative. And it's not a product rule anymore. It's an easier rule. And so it's going to work this time. So we'll have 1 over x over 2, right? Which is 1 over 2x. What happens if we plug infinity in there? Quote unquote, plug it in, right? You can't really plug infinity in, but we would get 1 over infinity, quote unquote. What's that? What happens if
Infinitely close to 0.
Infinitely close to 0, right? So that's 0. It's approaching 0 as x goes to infinity. And so what we just showed here is we need to apply the L'Hopital's rule 2 times. So to Rashid's question, we were originally trying to find this limit. That was the problem we were given. And it turns out that's the same thing as the limit as x goes to infinity of 1 over 2x. Right? We did L'Hopital's rule twice. So that ends up being 0. Sort of a summary. We had to do it twice here, right? That was the point of this particular one. What do you think? All right, there's one more on this page here. As I mentioned, it'd be good if you could try this one. And I believe you're going to need to do L'Hopital's rule on this one twice as well. All right, so if we tried just to plug in 0, right, so we're approaching 0 on this one. If we tried to plug in 0, we'd have 1 minus 0 minus 1 over 1 minus 1, and so we get 0 over 0. So we should apply L'Hopital's rule, which is taking a derivative. And if I remember correctly, it's not going to work the first time. And so you'll have to just do it twice. Not too bad. There is a trig function, but it's not bad. So anyway, let's take just a few minutes on that, and then we'll end this class just a little bit early. I will slowly start writing the answer down in just a moment here, but it would be good if you tried to apply L'Hopital's rule. Let me just pause here, and feel free to ask a question if something's not clear at this point. So I'll just take one derivative, make sure you're on the right track here. All right, so if we take one derivative, e to the x stays the same. X becomes 1. Cosine changes into minus sine. And 1 goes away. So it becomes that. But this is still no good, right? Because if you plug in the 0, you'd get 1 minus 1. And sine of 0 is 0. And so you get 0 over 0 still. And so you just have to apply it a third time. So just wait one more second to see how you do with that. And we'll look at the answer here. So this is an easy second derivative too, right? Because again, e to the x stays the same. 1 just goes away because it's a constant. Sine turns into cosine. Now, when you plug a 0 in, the world doesn't end, right? You'll get e to the 0 over minus cosine 0. And so that's going to be e to the 0 is 1, right? Cosine of 0 is also 1, so you have minus 1, which is minus 1. And so our original limit converges to minus 1. Took a couple applications of L'Hopital's rule, but no big deal. Thoughts about this rule? You know, you can see we're going to explore it a little bit more in some of the other indeterminate forms, but it's really no different than what we're doing right here. It's just going to be similar to this, just a little bit different. Questions about this? This homework and the related rates are the two things I've just posted for next week. Happy to look at some in class. Thoughts about it at all? All right, I'll stick around, see if anyone wants to talk about anything, homework or whatever, but that's all I've got today. I will see you in person on Friday.
Have a good day, Professor.
L'Hopital. L'Hopital. Where did you come up with that? Did you Google that?
No, I speak French.
Oh, gotcha. Is he French?
I believe it's French. It looks French. It looks like
It does
hospital
look French, yeah. For some reason, I thought he might have been from the Middle East, but maybe not. Anyway, L'Hopital. I don't buy that, but yeah, he is French.